Okay, example 4 here. Example 4 writes the functions in terms of y instead of x, but the same premise still applies. You're still doing top minus bottom, but if we kind of turn that into a horizontal, it's going to be right minus left. So we're trying to find the area of the region bounded by the graphs. X equals 3 minus y squared, so that's just a sideways parabola, so that is that graph. And x equals y plus 1. It's still a linear function, it's just in terms of y instead of in terms of x. So this is going to be our right, and this is going to be our left. We still need to find our points of intersection. Now, I know that we have the graph here, so let's visually investigate that. So we've got the point 2, 1 here, and we've got the point -1, -2. But if we didn't have the pictures, we would have to find this algebraically. So we need to set the equations equal to each other. This time, obviously, they're both equal to x. So since they're both equal to x, we can set them equal to each other. I would rather have my quadratic term to be positive. So I'm going to add the y squared to both sides and subtract the 3. So I've got y squared plus y minus 2. And when I factor that, I get plus 2 minus 1. So my 2 points of intersection are y equals -2 and y equals positive 1. Just like we would go left to right, we're going to go least to greatest on this when we're finding the area between the curves. So the area is equal to the integral from -2 to 1 of our right curve, 3 minus y squared, minus our left curve, y plus 1. And this is in terms of y. This would be dy. Notice my use of parentheses, especially since we're subtracting. I cannot emphasize that enough. That's where most people mess up. So let's simplify before we integrate. So we've got -y squared, we've got minus y, and we've got 3 minus 1, so that's plus 2. So when we integrate, we've got -y cubed over 3 minus y squared over 2 plus 2y, and we're going from -2 to positive 1. So let's plug in our limits. We've got -1 cubed over 3 minus 1 squared over 2 plus 2 times 1 minus, be careful with this, lots of negatives here. So we've got a negative that was already in front of the y, and the 2 is negative. So I'm being sure to put that in parentheses so that I don't mess that up. And I ran out of room there. All right, so 1 cubed is 1, but there's a negative in front of it. So that's a -1/3. And that's a -1/2 plus 2. Now, I'm not going to worry about putting those fractions together yet, because hopefully I'll be able to combine them with a fraction from the other part of the problem. So I've still got that minus. So -2 cubed is -8, but there was a negative in front of it, so that becomes positive 8/3. -2 squared is positive 4, but there's a minus in front of that fraction. And then I've got -4. Now, I know that 4 over 2 reduces, but why not leave it so that I can combine it with that other over 2? So we've got -1/3 minus 8/3, so that's -9/3. -1/2 minus a -4/2, so that's like adding 4/2. So -1 plus 4/2 is 3/2. And 2 minus a -4 is plus 6. -9 over 3 is -3. -3 plus 6 is 3. So if we put that over 2, that's 6. So that's 9 over 2. 9 over 2 is our area here. Now, if you wanted to check this using your calculator, obviously I just wouldn't use y's. I would use x, and I would go back to the very original problem here in case you made a sign error in distributing that negative, or the lack thereof of distributing that negative. And make sure you got your parentheses so that the calculator will do it correctly. But that's it. Okay, there's nothing different about it just because it's in terms of y. Don't let that throw you. Just remember you're talking about the y's instead of the x's. Notice that I did not use -1 and +2. Those were the x values. Okay. If I were trying to find the area between these two curves in terms of x values, guess what we would have to do? We would have to split it up because remember it's always top minus bottom. So here at x equals 2, that top function changes from being the linear function, which it was right here, to being the quadratic function. And it's kind of weird because over here, past x equals 2, we're really only talking about the area under the curve of that quadratic function. And if you look at it graphically, it kind of seems like these areas right here, I don't know why I just labeled them x, that's a poor choice of variables since we're talking about x's. It would appear that those have the same area because that is a symmetric parabola there. So anyways, totally unrelated, but I just wanted to point out the reason why it's easier to deal with this in terms of y instead of in terms of x is because the function that's quote unquote on top doesn't change for our region that we're talking about.